chiral centers. Do we have, what about this one? Can that be a chiral center right there?
Yes.
Yeah, that carbon, right? So what's attached to it? Let's look at the attachment, and then we're gonna go ahead and jump in and start dealing with enantiomers and mirror images and all that stuff. So what's the fourth group that's not shown?
The hydrogen.
The hydrogen.
Hydrogen, right? Let me move this down so I can blow it up. So there's a hydrogen. Can you still see that, Michaela?
Yes, I can.
Okay, cool. All right, so you got a hydrogen right here. It's on the dash, right? Anytime you have this tetrahedral like skeletal form and one of those groups is wedged, the other one is automatically dashed, right? That's a rule of thumb. All right, so I got a hydrogen on the dash, and let's see if we can figure out the configuration, because again, every chiral center is going to have a specific configuration. It's either going to be R or S, right? R means that the groups are oriented in a clockwise fashion. S means they're oriented in a counterclockwise fashion. Let me put that over here. So if I have a chiral center and it's got three groups on it, two is terrible, right? And I count to three like that. That's counterclockwise, right? So that configuration on that center would be S. So if the groups are oriented counterclockwise, it's S. And if you saw the video, you already have seen that. And then if I have the same, let me draw the same type of chiral center.
And with the numbers, that's priority, right?
Yes, that's the priority. That's exactly right. And then so here, if I go here, then that's clockwise. And so that's going to be R. Right. And that's, I'm glad you asked that question. So the numbers indicate the priority. So priority goes from 1 to 4, right? What's the lowest priority group that can be attached to an atom?
Hydrogen.
4.
I heard hydrogen, and then I heard or. What's the or?
I think she said 4.
Yes, yeah. So 1
Yeah,
is
4.
okay. I was giving too much credit. It's Friday though. I'm more liberal on Friday with credit. So you said 4, right? So 4 is the lowest. That's right, by the way. But I mean, in terms of groups, groups or atoms that are attached to a chiral center, what's the lowest? What's the lowest priority group that can be there?
Hydrogen.
Okay, I agree with that. But there's a group that's even lower than a hydrogen. What is it? So I will say that 8 is the lowest, but a lone pair is lower, right? So the only thing that's lower than hydrogen in priority is a lone pair of electrons. Are y'all following that?
Yes.
Yes.
So when we prioritize our groups based on atomic number, like we talked about the other day, right? We're prioritizing the groups that are around the chiral center. So let's go back up to the example, and let me erase all this other mess because we already dealt with that. What group? Well, first of all, let's identify the groups. So where are my groups that are on this chiral center right here? What's attached to it? What are the 4 things attached?
Which one? I can't see what you're pointing to.
The one with the highlighted in yellow.
Hydrogen,
bromine.
CH2, CH3.
So we got hydrogen, bromine. We have a CH3 over here and a CH2 over here. Everybody agree with that?
Yes.
Yes.
Okay. So now let's see if we can figure out the priority of those groups, and then we're going to determine the configuration of this center. And once we do that, we're going to talk about like I'm gonna give you a shortcut. It's a little bit different than what was in the video, but both methods are applicable. So if you had to prioritize these groups, what would be 4 automatically?
Hydrogen.
The hydrogen.
Hydrogen is going to be 4, right? And then what about what's going to be 1?
Bromine.
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 So now 2 and 3, priority wise, is going to be between the CH3 and the CH2. Is that right?
Right.
Okay, I'm starting off big, Super Bowl weekend. Which, if you can tell me, whoever tells me first which group out of the CH2 and CH3 is higher priority, I'm buying lunch.
CH3 has a higher
CH2.
priority.
So I heard 2 people speaking. So the first part,
It's CH2.
There's 2.
It's CH2 because it's attached to another carbon.
okay, I think I heard you say that. Someone else was talking at the same time. Who was that?
I said it was CH2. It's Joy.
What did you say at first though?
I just said it was CH2, and then she jumped in and said it's CH2 because blah blah blah.
No, we got to pick another example. I should have had my my little grid up so I could see who said it first. Next time I will put it in the chat. But we'll do the same thing with another example. All right, but it is the CH2 that's going to be higher in priority. Can somebody tell me why? I heard the answer, but why is CH2 on this side higher in priority than the CH3 on this side? How do we determine that? Because they're both carbons, right?
I think Amara said that it was because the CH2 is attached to another carbon.
Yes, you go to the next atom, which is here, and it's a carbon. Let me change the color on that. And if you go to the next atom over here, it's messy, sorry. It's a hydrogen, is that right?
Yes.
Yeah, so that's how that becomes higher in priority than the CH. Well, that's why that's higher in priority than the CH3. All right. So now we got our atoms prioritized. Let me go down here and see if I can paste this again.
Will the added element like bromine always be the first priority?
It depends on what you're comparing it to. If you got another atom in there that's higher in priority than bromine, then no. But if you're comparing it to carbon, then yes.
Okay.
All right, so let's see if we can figure out this configuration. So that's 1, that's 2, that's 3, and that's 4. Everybody agree with that?
Yes.
Okay, so the key to determining configuration, the old school way to do it, is to turn the molecules so that all you see is the top 3 atoms. So in this case, this would look like this, where this is bromine, this is carbon. I'm just going to write it as CH2, and then this is CH3, right? So that'd be 1, 2, and then 3. So I'm basically rotating it in space. So rotating it around in space just a tad so that the H is pointed back. The 4th group is pointed away from it. Did y'all see that in the video?
Yes.
Okay. So when I do that, now this is in what's called a steering wheel. So now I can figure it out anyway, but I just want to show you this, the steering wheel also, right? So if I count to 3, which way am I counting? Clockwise or counterclockwise?
Counterclockwise.
Counterclockwise. Good. So the configuration on this stereoisomer is going to be.
Yes.
Are we okay with that?
Yes.
Okay. Any questions about it? Let me add another page while I'm waiting on a question to be asked.
I do have a question though.
Come on with it.
When you're like talking about priority and you have like a wedged atom like hydrogen in this case.
Mm-hmm.
Oh wait, you don't count it in priority when you're counting, right? Like, or is it just the 4?
No.
So,
You have to prioritize it, but when you're trying to determine if it's R or S, it doesn't matter. It doesn't count. You only look at the top 3 groups.
Okay, because on the quiz I saw like a question. I think it was like number 4 and 6. Like that confused me about that.
Yeah, the low priority group is always pointed away from you, and you prioritize based on the top 3 groups. That's where the 3D orientation is going to come from.
Okay.
All right. Any other questions? All right. So that's S. So now let me ask this question. All right, you got to put it. I'm gonna watch the chat. Well, let me not yet. Too soon. It's got to be something more challenging. So how many stereo centers does this molecule have? I'm gonna paste it back down here again. We just gonna work the crap out of this example until we're satisfied with it. How many stereo centers?
2.
Okay, I heard an answer. And
I
remember,
agree with it.
stereo centers, chiral
Because
centers,
it's 2 to the N.
interchangeable. Okay. I think I hear you, but I think you're jumping the gun, but you're right in a sense. So here I'm asking how many stereo centers are
There's
present?
one.
One. Good. Now, so that's one stereo center. So how many stereo isomers are possible?
I see. No, it's 2.
You following that?
Yes.
So stereo centers are the number of chiral centers that are present. Stereo isomer is going to be 2 to the n, where n is the number of stereo centers. So this is going to be 2 to the 1, which is 2. Yes or no? We're good on that?
Yes.
Can you explain that? I'm kind of confused.
About which part?
The stereo center, like, where did they get 1 versus 2?
Okay, so the stereo center is a chiral center. It's an atom that has 4 different groups attached to it, non-symmetrical. You following?
Okay, so in this case, it's only 1 for the
Only
bromine.
one. We already picked that one out, right? Earlier we said
Right.
it's just this one, right?
Okay.
Yeah. So it's got 1 stereo center. That means that's the capability of, or the possibility of 2 stereo isomers. Because remember the definition of stereo isomers: same structure, different 3D orientation.
Right.
Is that right?
Mm-hmm.
Okay. So now we're going to talk about the other stereo isomer, what it is, and the relationship to the original structure. So the other stereo isomer in this case is going to be the mirror image of it, what we call the enantiomer. So I'm gonna draw both of them out. I'm thinking this pen up just a tad. So I got this. So here's my bromine. Everybody okay with that? Just the same thing that's up top. Is that right?
Yeah.
And then in the
Yes.
mirror image, I can draw it this way. Do y'all agree with that? Isn't that just like holding my left hand up against my right hand and looking at it?
Yes.
Everything stays the same. I don't change anything. So this is the mirror image. This is what we call the enantiomer. Remember that one of the criteria is to have a non-superimposable mirror image. Is that right?
Mm-hmm.
One of the criteria for a molecule to be chiral is that it has a non-superimposable mirror image. So it has a chiral center with 4 different groups attached. It's non-symmetrical. It's sp3 hybridized, and it has a non-superimposable mirror image. That's a criteria for chirality. So that the second stereoisomer is the enantiomer of the first. Are we okay with that?
Yes.
Okay.
Yes.
Now, when you're asked to draw the mirror image, you can draw it this way, which is no problem, or you can draw it like this. Let me give you the second option. So I can draw it like this. I'm gonna change the color. Right? Are y'all following
Those
that?
two would be the same thing,
Same.
technically.
So these two, you see where the arrows point, the little pink arrows pointing back to the mirror image?
Mm-hmm.
Yeah, those are the same. So what did I do to the mirror image to make it look like this? What did I do to it?
You changed the,
I guess she like rotated it,
Turned
probably.
it over. I flipped it over. Can you see how now the atoms can line up? Let's see if I can get a good color.
Yeah.
Right here, right here, here, here. You following that? You can line all those atoms up now. This is when I draw it this way, I'm drawing it in the superimposed image. That's the superimposed image. So I can lay it on top of the other image. You following? I can lay this one on top of this one. Now the question is, are they gonna lay flat against one another? Like will you be able to line all the atoms up?
Yes.
no.
So one yes and one no. Why did you say yes? You don't see the difference in the chiral center? You see how the top one is wedged and the bottom one is dashed?
Yeah, that's what I was talking
Okay, that's okay.
They're not going to lay on top of each. All the other atoms will, but the chiral centers won't match. You following? So
Yeah, I got it.
that's the enantiomer of the original image. We're gonna call it A. So this is A, and then this is B, and this is also B. Right? It's just turned over.
So would the hydrogen have
A wedge.
a wedge?
Mhm.
Yeah.
So I'm trying to get you to see something without saying it, but we're gonna say it now. Do you see in the original image A and the mirror image B, what happened to the chiral center?
It
Flip.
moved.
It's
Flip.
reversed, isn't it? Or inverted. Is that right?
Yeah.
So that's for any enantiomer, any mirror image, whatever the chiral centers are in the original image, it'll be reversed in the mirror image. Does that make sense?
Yes.
Yeah.
I'm gonna write that down
You
here.
said it one more time.
I'm gonna write it down. So the chiral centers are inverted. Let me not say inverted. I'm gonna say reversed. In the mirror image. So any mirror image that's an enantiomer, the chiral centers are gonna be reversed.
Dr. Russell.
Yes.
So both of the ones you put at B on as B, are those both the enantiomers?
Yeah, it's the same image. It's just turned over. It's not it's not an additional image. It's just the B that's up here flipped over.
Okay.
Are you following? I normally do an example when I'm in class. I'll have like two people stand face to face and try to put their arms out towards each other like each one is a chiral center. And then when you turn the other person, one of the subjects, if you turn them around, you'll see that the chiral center is reversed, but it's not a new image. It's the same image. It's just turned over.
Okay.
Does that make sense?
Yeah, I just wanted to make sure I got the vocab correct. That
Okay.
they were both the enantiomers.
And the only difference is one bromine is going out and one bromine is going in, right?
Yep. So now let's go. Let me ask you this question. We already proved up here that the configuration for that chiral center is S, didn't we?
Yes.
So what's the configuration for the enantiomer? Without having to go through the steps, what is it? What do you think it is?
Would it be R?
Yes.
It would be R, right?
Yes, it has to be, right? Because B is the mirror image of A. So if the configuration of the stereo center in A is S, by default,
It's opposite.
enantiomer is the opposite.
Now, Dr. Russell, I was watching the video and
Uh-oh.
it was saying something about if hydrogen is wedged, then
Then you reverse it.
yeah, I think so.
Yeah. We're going to talk about that in a minute. We're going to do another example.
Okay.
Yeah, we're going to do another example. All right,
What?
Go ahead.
What is the 2? I think you wrote like 2 something equals 2 1 equals 2. What does the first 2 something say?
Where is it? Right here?
Mm-hmm.
Oh, that's an exponent n. Sorry.
Okay.
My handwriting is bad. I know it. I've been
It's
working on
okay.
it since kindergarten. I ain't got it yet.
Is that like a specific formula?
Yeah, that's how you determine the number of stereoisomers for a given compound.
Oh, okay.
N is the number of stereocenters.
Okay.
If you look at the notes from Monday, was it Monday? What's the day? Friday? Wednesday. Look at the notes from Wednesday. It's right here. It's on the second page of the notes from Wednesday.
Oh, okay.
Mhm.
Thank you.
Mhm. All right, let's pick another example. I want to do one with more than one stereocenter though, so we can talk about another concept. And I need to make sure that this is not a meso compound. Maybe I should draw my own. Ooh, that's a good one right there. Let's get this one. All right, I'm gonna put that on a new page and we're gonna walk it down. And then I'm gonna also introduce you to another idea. And then we'll come back to the Fisher projections. Are we all right? We're not moving too fast, are we? Let me know.
No, I think we're okay.
All right.
No, it's the case.
Let me know. I only have 2 speeds, 0 and 100. Come on. All right, let me make sure that, yeah, okay, that's a new page. All right. So I'm gonna paste this image in here. Can y'all see the wedge and the dash, the difference between them?
Yes.
Okay.
Yes.
All right, I just want to make sure. All right, let me get this off of here. All right, so let's do this. Let's rule out everything that can't be a chiral center first before we start identifying chiral centers. All right.
I have a question.
Go ahead.
I thought you said if they give us the dash and the wedge, those start our chiral centers.
Yeah,
Okay.
but practice makes perfect. So what's not chiral? Is this carbon? Can that carbon be chiral
No.
with 3
No.
CH3s attached? No. What about that one?
No.
No.
None of those. None of the CH2s, and then the oxygen can't be either because it's got 2 long pairs on it. Is that right?
Yes.
Yes.
All right. So now we got 2 chiral centers that we're dealing with. We got one here. I'm gonna write in the CH3, and we got one here. One day.
Okay, this might be a slow question, but how
Okay.
do you know that's a CH3 again?
The end of every line in a skeletal form is a CH3, and every vertex is a CH2. That's not a slow question. That's a good question. I don't believe in slow questions. If it's on your mind, ask it. That'll keep you from getting tripped up down the line. All right. So which one do you want to attack first?
Probably the wedge.
The wedge. All right, let's do the wedge. All right. So we found the chiral center. Everybody agrees that that's a chiral center right there, that carbon. And it's got 4 things attached to it that are different. Is that right? It's got a CH3, it's got a CH2 on either side, and there's a hydrogen going back. Is that right?
Yes.
Yes.
And then over here, there's a hydrogen where? Coming up. Following?
Yes.
Yes.
Oh, that was slow. All right, that's all right. We're gonna get it. We're gonna get it. We're gonna get it. All right. So we're doing the wedge one. Let's prioritize it. Which one of those carbons do you think is one?
The
Let's
one
see.
with the OH.
All right, let's find out. So let's look at it. So this carbon and this carbon is what we're comparing. And since they're the same, you got to move to the next atom. Is that right?
Yes.
So we move to this atom right here and this atom right here. Is that right?
Yes.
Now I know this is going to sound weird. It's going to sound really weird, but the carbon where the branch is going to actually going to be higher in priority. Everybody got quiet.
Why?
It's one of the IUPAC rules. If it wasn't branched, if it was just a carbon connected to another carbon, it would be different. But the fact that there's a branch point, it actually is higher in priority than the other carbon.
Wait, Dr. Russ,
Yes. Go ahead.
I was asking if you could repeat what you said.
Yeah, so the two carbons that we're looking at right here, right? Those two carbons, because one of them is a branch point, that it's going to supersede the other carbon, even though it's connected to a hydroxyl group.
Dr.
Is
Russell?
that in every situation or just this one?
In this situation.
Okay.
Go ahead.
So it's a branch point because of the wedge?
Yeah, but can you see that carbon that I have highlighted? It's got if we drew it without the wedge or without the dash, it would look like this. You follow me?
Yes.
Whereas the other carbon will be here, right? Follow me?
Mm-hmm.
So the branch carbon is going to supersede it. I know it sounds weird because there's an oxygen there, but that's just the IUPAC rule that we have to follow.
Okay.
If it was wedged, would it still be the same?
It would still be a branch point.
Okay.
Mm-hmm. All right. Are we good so far?
Yeah.
So which one of those is going to be one? Because we know the hydrogen is 4, yes?
Yes.
And we notice the CH3 is not going to supersede any of the other two that I have boxed in because it's a CH3. So that's going to be 1 right here. Is that right?
Yes.
And then this is 2. And then this is 3. Is that right? Are we clear on that?
I guess I need further explanation of why.
Why the 1 is 1?
Yes, and the 2 is 2.
When we look at those two carbons that are boxed in, right? We can't make a determination on their priority because they're the same atom. So we have to move to the next atom. Are you following?
Yes.
So the next atom is carbon. Is that right? Where the arrows are? Do you see where the arrows are?
Mm-hmm.
On the carbon that's on the right, that's attached to 1, it's branched. Right? Even though the CH3 is on a dash, that carbon actually looks like this right here. Let me fix that too. You following that?
Yes.
So that the fact that this carbon right here is a branch point and this one isn't, that makes that side higher in priority.
Okay. I just thought the 1 meant it was the lowest priority. So how is
No. 1 is highest, 4 is lowest.
okay? It makes a lot more sense. Okay.
Let me go back here because we wrote it down right here. Priority is from 1 to 4. 1 is the highest, 4 is the lowest. And H is the lowest priority group atom. And then the only thing lower than hydrogen is a lone pair.
Okay, thank you.
Okay, you got it?
Yes.
All right. So
Wait,
now, come on.
Oh, okay. So normally it goes 1 through 4. Are we not putting 4?
We don't
Or
need it.
is it because they're the same thing, the CH3?
No, because
Oh, the hydrogen.
hydrogen is 4, but we're only concerned with the top 3 groups when we get ready to do the configuration.
Okay.
We don't count 4. You follow me?
Yes.
All right. So if we were to count that, which way is it going? Clockwise or counterclockwise?
Clockwise.
Clockwise.
It's going like this, isn't it?
Yes.
So is that R or S?
R.
So that means
R.
this is R. Great. Yeah, I'm glad y'all are engaged. And we got a full house today too. That's a blessing. Thank y'all. If you came late, make sure your name is in the chat box so you can get credit for being here. Go ahead.
So how do you know you said clockwise? How can you tell that? I'm sorry, I never.
So that's okay. Count to 3. Start at 1 and count to 3. You see where 1 is? 1, 2, 3, like this. Let me change my pen so it doesn't look so weird. Right. So I'm counting to 3 like that.
Okay.
Following?
And then you said if it's clockwise, it's R.
Clockwise is R, or right hand, or rectus in Latin. And then counterclockwise is left hand or sinister in Latin. So that's why we call it S.
Okay. Thank you.
I'm gonna put this here too.
I have a question.
Go ahead.
So, you said the chiral center has 4 different substituents, right?
Yes.
So this one, is it still considered that even though it has 2 CH2 just because of the dash and the wedge?
Good question. But are the 2 CH2s identical? That's the question you have to ask yourself.
Oh, it's because it has the stuff on the end?
Yes. They're
Okay.
both connected to something different. So there's no symmetry. So the 2 CH2s are not the same.
Okay.
No, good question. Are we okay with that?
Yes.
I have a question about it.
Well, go ahead.
So going from this carbon that's below the CH3, branch point.
Say that one more time. You kind of cut out at the end.
So going from the carbon that's below the CH3, regardless of the branch point, where would it go next?
I'm not sure I understand the question. So you're talking about the chiral center that I have highlighted, right?
Yes. No. The one that's under the staircase.
You talking about on the right side?
Yes.
Okay. Let me see if I get if I'm understand. You're talking about this carbon right here.
Yes.
Okay. What you said? Where would it go next?
Yes, regardless of the branch point, because I know that the branch point is on a higher point, but where would it go next?
It doesn't matter.
Okay.
When you have 2 of the same atoms attached to a chiral center, you just keep going until you reach a point of difference. Right? Okay. And so for the carbons that are listed as 1 and 2, the point of difference was the next carbon.
Okay.
If that branch wasn't there, then we would keep going to the next atom until we reach the point of difference. Does that make sense? All right. So the branch point is it's kind of tricky when you're doing configuration, determining the priority of those carbons that are branched versus non-branched. But I think that's why I picked this example, so we won't get stuck on there if you see it again.
Can you point out the branch point again?
Yeah, it's right here. It's the one I have highlighted in green right here.
Okay.
Right. If I were to draw that without the stereochemistry indicated, sorry, it would look like this. So it would be, let me just draw the whole thing. And then put on here. Yeah, it would look like that. You following? Remember I said the other day, if the lines are straight and not wedged or dashed, then that means that the stereochemistry is undefined. We don't know if it's RS. Okay. So do you see the difference now in these 2 carbons? This one, not that one, sorry, wrong one. This one and this one. You see the branch, the difference?
Right.
Yeah. All right, we're good on
I
that
have
side.
one last question.
Go ahead.
If you would have started with the dotted wedge, would the answer be any different?
Oh, it's gonna be different because it's a different orientation. It may still be R, depending on how the groups are prioritized, but we're gonna apply the same thing on that one that we did to the other one.
Okay.
It's still the same group wise, it's still got 4 different things attached to it. So we're only concerned about those 4 groups.
Okay, thank you.
Dr. Russell,
Yes.
so there was just one chiral center, or both of those were the chiral centers?
No, they both are.
Okay.
We just haven't got to the other one yet.
All right.
All right, we're good so far? Y'all ready to do the next one? The next chiral center?
Yeah.
All right. I'm gonna repaste it because I don't want to delete it, and then when you go back and look at the notes later, it's only one example in there. So I'm gonna repaste it here. I'm gonna do the other one. All right, so now we're doing the chiral center on the right side, this one. So we got a CH3 right here. We got a hydrogen coming up. Everybody agree with that? So let's prioritize. Now you know the CH3 out of the 3 carbons that are attached. How you think CH3 is going to rank?
Would it be the third?
Third
Gonna be
one?
the third out of all of them. That's exactly right. So I'm gonna go ahead and put a 3 right here and a 4 right here. Now we just need to pick between these two, which one is 1 and which one is 2. What do you think?
I think the branch would be 1 because of the rule you're talking about.
Who is that that's about to get a fist bump through the screen? You said the branch one is going to be 1?
Yes.
I agree. Because it's branched, right? Compared
Absolutely.
to the other carbon. So this is 1, and then that's 2. Great. That's great. See how that example on the other side helped us to do this one? So now it was no question about whether it's, oh, well, I don't know because it's this, is that. No, it's a branch point. The other one doesn't have a branch point. Boom. So now you're able to prioritize it a lot faster. Following?
I'm confused.
Go ahead.
Okay, so on the other way, I don't know. Like, can you explain why? First of all, this one is just, I'm just confused. I don't know what's going on.
Yes, you do. Don't tell yourself that because you're going to go to get off the Zoom thing.
I got the first one.
Mm-hmm. So what's the difference in this one? We're just looking at a different chiral center. You agree with that?
Mm-hmm.
And the substituents are different. Right? The 4 things that are attached are different, but the same principle applies. When you look at the carbon that's labeled 2 and the one that's labeled 1, what's the difference between them? One of them has 3 CH3s attached to it, doesn't it?
Right.
Right? Like a tert butyl. You remember that from part 1? Tertiary butyl. Yes. Yeah, like that. So that when you compare those 2 carbons, the carbon that's labeled number 1 is branched. That's what we call it. When it has multiple methyl groups attached like that, we just call it a branch point. Or multiple carbons attached to it, we call it a branch point.
Okay.
So that carbon that's labeled 1 is branched. The one at 2 is not. So 1 is going to be higher in priority.
Right. Okay, I get it.
Mm-hmm. Told you. All right. Can we count to 3?
Mm-hmm.
Is that clockwise or counterclockwise? Let's see.
Clockwise.
We're counting from here. 1.
Dr. Russell, I can't hear anything.
Huh? My audio, is anybody else having trouble hearing me?
I can hear you fine.
Who?
No.
Who was that?
I think that was.
Yeah, I don't have the grid up, so I can't see who's talking.
Yeah.
All right. Let me put it. I'm gonna put it in the chat right quick. Yeah. Let me try recycling my audio. I'm gonna turn it back on. Can y'all hear me still?
Yeah.
Yes.
I don't know who that was. Hopefully her audio came back up.
I got it back. I don't know what happened. I was like,
All right,
what?
cool. Thank you. Thank you for letting me know. All right, so we got our groups are here, and we count to 3 like that, right? So that's clockwise. But the problem is the H is wedged, right? Normally you want H pointed away from you. So the shortcut is if H is wedged like this, whatever you see, you have to reverse it. So if you see it being clockwise, you see how the numbers are oriented clockwise, that would normally be R, but the fact that H is wedged, we're going to call it S. Following? Now I could show you that too, if it'll help.
So this is considered a Fisher projection?
No, it's not a Fisher projection, but it's the same principle. It's the same principle.
Okay.
Because we want H away from us, right? To determine the configuration. But since it's not, since it's pointed at us, we can just reverse what we see. So if the H is pointed out at you, this is a shortcut. If it's pointed out at you, then if it's R, the actual configuration is S.
Okay, thank you. Because I was getting a little tripped up on the quiz.
Yeah.
And it wasn't a Fisher, but now it makes sense.
Yeah, let me show you though, because I don't want you to think that I'm just BSing you. So if I draw this, I'm just gonna put my other groups over here, right? So I'm gonna make this 1, I'm gonna make that 2, and then the CH3 is 3. You following? Yes or no?
Yes.
All right, if I turn this over so that H was pointed to the back, it would look like this. You following?
Mm-hmm.
Now, what's the configuration? Right? You see now it's counterclockwise?
Yes.
You following?
Mm-hmm.
But you don't, but there's a way to avoid that step, and it's just to remember the rule of thumb that if H is pointed out, then you reverse the configuration.
Right. Okay.
You following? But yes. Now when I first started teaching this, I would teach it and bring the models in and have people sitting there rotating stuff. This is one of the hardest skills to acquire is to learn how to see things in 3D. But it's good practice. That's why I recommend having a model set, because then it makes sense. It makes a lot more sense.
So basically, if the H is wedged out, it'll be S, or if an atom is wedged out, it'll be S, or the opposite of what it would have been.
Opposite, yes, it's the opposite. Are we okay with that? So that's S. Let me paste this thing. Let me add another page.
Dr. Russell, when you say out, you mean horizontal, right?
Say that again.
When you say out.
No, don't confuse this with a Fisher projection. A Fisher projection has horizontal and vertical. We just haven't done one yet, but it's a good place to do one. Let me add another page right quick. Yeah. So here we're still talking wedged and dashed, and not necessarily horizontal and vertical. Does that make sense?
Yes, sir.
Because really both of those are vertically oriented, right? The CH3 and the H are both vertical. They're both pointed up, but one of them is just pointed into the page and one out of the page. Are you following that?
Yes.
Okay. So we're gonna put this example down here one more time. Might as well walk it down while we got it. So we already agreed that this was, what did we say the first one was? R? Or was it S?
It was R.
Okay, and this is
S.
S. Everybody agree with that?
Yes.
So we figured out the configuration, we figured out all that. Now let's push it. How many stereoisomers are possible for this molecule? Let me write that question down. I heard somebody say it already. Boy, y'all on fire today. How many stereoisomers?
4.
4.
4.
Right? Because it's got 2 stereocenters. So 4 stereoisomers total. Everybody okay with that?
Yes.
Yes.
Okay, here's the question. We got one right here, right? What do you think the second one is?
Some of the stereoisomer.
Yeah. We gotta come up with 4 different isomers, right? We already have 3 other ones because we got one. All right. Let me
So 4 is only how many is possible. It's not going to always be 4.
Oh, it's got to be 4. It's got
Oh,
to
so
be
just
4.
got to prove it.
Mm-hmm.
So could you reverse like the one that's wedged?
flip
Could
it?
you make it dashed? And the
You
other
can do
one
that,
wedged?
but I'm trying to get you to recall what we've already done first. What could we draw immediately and get that second stereoisomer?
The mirror
The
image.
The mirror image.
image.
Can we just draw the mirror image and that's immediately the second isomer?
Yeah.
Is that right?
Yes.
Dang it. Sorry. Right? This is the mirror image of that. Do you agree?
Yes. Wait.
If I held up the one, we're gonna call it A. If I held up A in a mirror and to look at itself in a mirror, this is what it would see. Am I right?
Right.
When you look in a mirror, don't you see your nose first and not the back of your head?
Mm-hmm.
Or that's just like this looking at itself. Yes or no?
Yes.
All right.
Yes.
So that's my second one. All right. And what's the relationship between A and B?
Non-superimposable.
Good. Okay, good. The short term for that is what? Enantiomers. Following?
Yes.
Mm-hmm. So the third and the fourth isomer are going to be, let me see if I can copy this because I don't feel like redrawing it. Well, I'll redraw it. Let's see. Well, we got 5 minutes left. Come on, pen. Uh-oh. Okay, so this is we can see what the original is. The other 2 isomers are going to be, they're not going to be enantiomers of A or B. They're going to be different. They're going to be, I heard somebody say it, like what you could do, but I don't think, we didn't talk about the terminology. The other ones are going to be what we call diastereomers. Right? So if I took A and I changed this wedge to a dash, I'm sorry, change the dash to a wedge. That's so sloppy. Sorry, I got to fix that. If I change that to a wedge like that, you following that? That's one of my 4 isomers. Oh, let me put my OH in, my bad. Are y'all following?
Yes.
So you see I left the wedge one, the one that's R, I left it.
Right.
And then the other one, I changed it.
From the dash.
Yes, to a wedge. So a diastereomer is not a mirror image, but it differs by one, you change one stereocenter. That's how you get a diastereomer. You need at least 2 stereocenters to be able to have diastereomers though. Like if you only got one stereocenter, then you only have enantiomers. But the minute you have more than one stereocenter, then you have the you can also have diastereomers in addition to enantiomers. Are you following that? So what were the other? That's 3 images we got. We got the mirror image. We got 1 diastereomer. What would the other image look like?
It'd be 2 dashes instead of 2 wedges.
Come on, child. Come on a good Friday. I could change that to a dash, couldn't I? And then leave this dash how it is. And that's my other diastereomer. Let me fix that because that's sloppy. I'm gonna write that definition in before I post these notes. All right. Do you agree? Is that
Yes.
is that full
Yes.
stereoisomers?
Mm-hmm.
We got the A and B, and then we're gonna call this C and D. Now, here's the thing. C and D, when you compare them to A, they are diastereomers of A. Are you following? Because they're not mirror images. They're still chiral. They still have chirality, but they're not mirror images of A. So when you compare C and D to A, they're diastereomers. What is the relationship of C and D to each other?
Enantiomer.
And that they are, aren't they?
Yeah.
Let's do this before we close out. We got 1 minute. What's the configuration on B of each of those chiral centers?
S and R.
What would this one be? This one would be R, wouldn't it?
R.
Because the mirror image has to be what? It's got to be the exact opposite of the original. Are you following?
Yeah.
Yes.
So where the wedge over here is R, it's got to be S on the other side, on the mirror image. And whereas S has got to be R. Does that make sense?
I have a question,
Yes.
Dr. Russell.
Go ahead.
Maybe I wasn't paying attention, but so
Uh-oh.
every wedge. I'm sorry.
Uh-oh.
No, I was, but I get kind of lost. Okay, so
It's sarcasm. No, I'm just go ahead.
The wedges,
Mm-hmm.
will those always be R?
No.
Okay. Never
R
mind.
is on R and S is based on the priority of the groups around the chiral center. That's how you determine if it's R or S.
Okay.
All right. Everybody agree that this C should be RR?
Yes.
And then do you agree that this one should be, do you see how we don't have to go through the exercise now since we did the first one? This one will be S. Do you agree with that?
Yes.
Mm-hmm.
Yes.
And C and D are enantiomers of each other, but they are diastereomers of A or B. I'm gonna write that in here before I post this to Blackboard.
I have a question. RNS, I don't know how you say it. RNS for the diastereomers.
The diastereomer.
Okay, so RNS for those would be the opposite, or does that correlating to figure A for the enantiomer? Okay.
Yeah. See, once we found the stereo centers, the configurations in A, all the other configurations we can base it off of what we already know for A.
Okay.
So if the one where in A that's R, if we change that from wedge to dash, we know it's going to change from R to S. Because we just reverse it, right? All right. Any other questions? I know some of y'all got class, so I don't want to go over again.
Dr. Russell, I want to see if I can stay behind and ask you some questions.
Well, I have another class at 10, but yeah, I can stay for a few minutes.
Okay. I got a question about the in-class assignment.
Mm-hmm.
So you just want us to type it on the PDF?
You can write it in, handwrite it, type it, scan it, however you want to do it.
Okay. And when do you want it submitted by?
Well, we always submit the in-class work when we turn in the exam.
Okay.
So right now, what we did today, we're going to go back to some of these other examples. We're not going to be able to do every single example, but I'm going to pull some out where we have to figure out the configuration, that. We'll probably do that Monday. And then we're going to hit another topic on Wednesday, and the exam, which is supposed to be on the 17th, I think I said the 17th in the syllabus. It may or may not. It depends on how far we get. It may get moved another day up or a couple of days up.
And for the in-class assignment, do you want all the problems done or just the ones we go over in class?
The ones we go over in class and anything I tell you to finish outside of class. So like if we don't finish everything, but I say do 5.5 A, B, and C, then I'm expecting to see that when you turn it in.
Okay.
Yeah, and you can ask questions about it just because you're not doing it in class. When we do recitation, you can ask questions in recitation. When we do, you know, if you want to do office hours, you send me an email, whatever. You're not just, I ain't throwing you to the wolves, but I'm saying those are the ones I want you to try on your own.
Gotcha.
Yeah.
Thank you, Dr. Russell.
All right.
Okay, Dr. Russell, I have an issue.
Uh-oh.
So it's pairs, right?
Yeah.
And so I have a class conflict on Fridays with your class.
How?
So I have a lab for biostats from 8 to 10.
Okay.
Just on Fridays. What should I do?
What do you think you should do?
I mean, I came in late today, but I'm like, you know, I be playing sometimes. I'm trying to be serious this semester. I took a year break.
Be serious, time to be serious. Let's talk offline. I think you can make it work because all the lectures are recorded. So on Fridays, if you are in your lab, you know, you can just watch the recording and then take notes from that and ask questions.
Okay.
Yeah, that's the flexible answer. Now the other answer would be, well, you need to drop the class, but
I'm not doing that.
Nah, well, I said the non-flexible answer. I'm giving you the flexible answer first because we can work around it.
Okay. Thank you, Dr. Russell.
All right.
Dr. Russell.
Yes.
Oh, before you start, Mario, you said, Dr. Russell, you said you only have